All right, now as an astronomer, when I receive light from across the universe with my telescope, now I need to be able to interpret it. What's creating this light? Where's this light coming from? What does this light tell me? So I guess the question is, how do you make light? How do you, or how does anything, make light? If you want to create light, what do? Well, you turn on the light switch. I mean, okay, but how do you make light in general? Well, one way of there are a couple of ways to make light. You know, one way, get hot. So if I take an object and I heat it up enough, it will tend to glow. Hot things tend to glow. And when we study the light given off by hot, glowing, opaque objects, we find that there's a certain very distinctive, interesting pattern to it. So this type of light we're going to talk about. So we're going to talk about, get hot. So we're going to talk about light from glowing, opaque, O-P-A, if I can write here, Q-U-E, opaque objects. Okay, first of all, glowing. Okay, glowing means giving off light, fair enough. Opaque. Opaque, what does opaque mean? Opaque means you can't see through it. Opaque is the opposite of transparent. Something is transparent if you can see through it, like air is transparent. A plate of glass is transparent. You can see through it. Opaque means you can't see through it. It's a wall. It's me. I'm opaque. You're opaque. Stars are opaque. Planets are opaque. Anything that you cannot see through it is opaque. So we're going to talk, there's some very big differences between light from opaque objects and then light from thin transparent gases is going to be the other thing we're going to talk about. You can see a gas, but gas can also give off light too, and we'll talk about that later. But for right now, I want to talk about light from glowing opaque objects. Objects thick and dense enough that you cannot see through them. And so what I find is that all opaque objects are always emitting, giving off, glowing, emitting what we call a thermal blackbody spectrum. So, and this is an interesting thing. And it turns out that all opaque objects, I'm an opaque object, you're an opaque object, the sun is an opaque object, the earth is an opaque object, all opaque objects are always emitting a thermal blackbody spectrum. Now the light you're seeing, the camera's picking up from me, that's not what I'm talking about, because that's reflected light. And I'm not talking about reflected light here. By saying emitting, I mean it's giving off because I have some warmth to me, and so I'm giving off this light. A traditional light bulb with a little tungsten filament in there, the electricity runs through the filament, makes it hot, and then that filament glows and then that lights up the room. That's what I'm talking about. The light given off by the sun. The sun's an opaque object. This is what I'm talking about. And so what I find is I find a continuous spectrum. Continuous spectrum. Meaning lots of different wavelengths. Lots of wavelengths. You heat up a light bulb and so it glows, and you don't just get, green or yellow or red, or no, you get a whole spectrum of colors. You get a full rainbow. A full rainbow of colors. You get energy at many, many different wavelengths. You get some longer wavelengths, some shorter wavelengths. You get this broad spectrum, a continuous spectrum of light. And when I make a graph of this, it turns out to be really interesting. Let's take a look at this. All right, so what I'm going to do is I'm going to make a graph, and on the horizontal axis, I'm going to plot out wavelength. Wavelength. So on the long end, this would be, this would be long wavelengths, and this would be short wavelength. So I don't know, maybe the visible range is here. Here's red, orange, yellow, green, blue, and violet. And on this axis, I'm going to plot intensity. Intensity. Brightness. So I'm going to say, well, how much energy am I receiving from this light bulb in terms of red light and green light and orange light and yellow light and blue light, or infrared light, or I guess over here would be ultraviolet, here would be infrared, and it's distributed across all these sorts of things. So what does it look like? And when I plot this, I can get a nice graph, and the graph goes something like this. And so basically, this is just a quick sketch. But the graph is a nice smooth curve with one peak. One peak. So what this graph says, aha, where is this light the brightest? Oh, it's brightest in the yellow. It has the largest intensity right here where I put the yellow part of the spectrum. It has some red light, it has some violet light, it has a little bit of ultraviolet light, it has some infrared light. And so what I do is I say, so the thermal, this is a thermal blackbody spectrum. This is a thermal blackbody spectrum. So this is being given off all the time by all opaque objects. Every opaque object in the universe is always giving off a thermal blackbody spectrum. So it is a smooth curve with one peak. There's one peak and then it decreases there in both directions. And what we find is a smooth curve with one peak, and that peak is determined by the temperature. The location of the peak, is it in the yellow, is it in the blue, is it in the infrared, is it in the ultraviolet? The location of the peak, in other words, the brightest color emitted is controlled by temperature. Controlled by temperature. So that determines what it is. I mean, think about this. Think about taking a bar of iron and you put it in a furnace and you heat it up and then hold it out. And when at first it doesn't glow at all. And then you get hotter and hotter and hotter. And then it starts to glow a dull kind of cherry red. And then you heat it up more and then it glows hotter. And then it can glow orange hot. And then it can glow yellow hot. And if you heat it up even more, it'll glow white hot. And if you heat it up even more beyond that, so you see it started out with a long wavelength peak, which coming into the orange, and then the yellow, and then you heat it up. White hot is where the peak's somewhere in the yellow-green part of the spectrum. And then if you heat it up even more, well, the bar of iron will melt. But if you keep heating it beyond that, you can even make it glow blue hot. And so one peak is controlled by the temperature. So if I had a cooler source, then I would find, so this is cooler. Notice the whole curve goes down, and then the curve also goes up, and the peak shifts toward the blues part of the spectrum. So this is hotter. This is how we know the temperature of every star in the universe. If I look at a star and I say, hey, there's a red star and there's a blue star, which is hotter? They're both opaque objects. They're both hot, glowing, opaque objects. So what does that mean? It means that the star with the peak emission in the red must be cooler than the star with the peak emission in the blue. And this is true throughout the whole entire universe. And this is true. This is how you can tell my temperature with that. I'm not going in the visible. I'm not warm enough to do that. I'm cool enough that my peak is off in the infrared. And that's how like heat cameras work, or those crazy night vision cameras and stuff like that. Those are working in the infrared. And so a heat camera looks at me and it's seeing my thermal blackbody spectrum, my heat energy given off, and that has a peak off in the infrared. And using this, we can measure the temperature of every opaque object in the whole entire universe. You look at that curve of that spectrum, and then you figure out where's the peak. And the peak tells you how hot it is. Redder, longer wavelength is cooler. Bluer, shorter wavelength is hotter. And here is something else that is that's absolutely wonderful. Thermal blackbody spectrum. Thermal blackbody spectrum. It has nothing to do with chemical composition. Has nothing to do with composition, what it's made of. If you take a bar of iron and a bar of aluminum and heat them both up to the same temperature until they're the exact same temperature, they will glow in precisely exactly the same way. It is impossible to tell the difference between your bar of iron and your bar of aluminum by their thermal blackbody spectrum. Now, they might reflect light in a different way, so maybe there's something we can get from the reflected light. But this thermal blackbody spectrum they're emitting, it has everything to do with its temperature and nothing to do with what it's made of. So with the one thing we can get out of is temperature, but then that's the only thing we can get out of it. We'll need other bits of spectrum to do chemical composition. And here's something else. The peak wavelength, the brightest wavelength, is related to the temperature in an equation we can use, and you're going to learn, and we can use this to calculate the temperature of every object in the universe. So the peak wavelength is related to the temperature, and we're going to measure the temperature in degrees Kelvin. In this class, we're going to measure temperature in kelvins. And people say, well, why do we have to use kelvins? Why can't we use good old-fashioned Fahrenheit or at least Celsius, you know, something like that? No, no, no. Here's why we have to use Kelvin. We use Kelvin because that's connected to what heat is, what thermal energy is. Here's what heat is. If I had a hot hot bar of iron and a cooler bar of iron, and if I were to zoom in on them with a super powerful microscope, the difference between a hot object and a cooler object is if you could look at the individual atoms in there. In the hot object, you would find those atoms are bouncing around a whole lot faster, and in the cooler object, the atoms are moving a little bit slower. Atoms are constantly in motion, they're constantly jiggling against each other and all this, but the hotter you get, the faster they move. And so, what does that mean? Well, this tells us something about temperature. Temperature is just the energy contained in the individual random motions of your individual atoms and electrons as they're all bouncing around together. Solid, liquid, gas doesn't matter. The faster they're moving, the hotter they are. And this is really interesting. And so this means that, I mean, you can always speed something up a little bit. You can always make those atoms move a little bit faster. And so as a result, that means there's no limit to how hot things can be. There's no maximum temperature. Something can always get hotter. On the other hand, there is a limit to how cold something can be. There's a limit to how cold you can be because you can never move any slower than stopped. That's the limit. And so the Kelvin system is based on that idea. There is a coldest temperature. You can't get any colder than absolute zero. Now in Fahrenheit, that's some negative temperature. In Celsius, that's some negative temperature. In Kelvin, 0 equals absolute zero. Absolute zero. At 273 Kelvin is where water freezes below it, melts above it. 373 Kelvin is where water boils. So room temperature is somewhere in the neighborhood of 300 Kelvin, and that's what we're talking about. And so that's connected to some real physical process. Now, okay, back to the thermal blackbody spectrum. There's a law which connects an equation which connects the wavelength of maximum emission, the brightest wavelength, and temperature is equal to a constant divided by the temperature in Kelvin. And it says, what you do, it's 2,900,000 nanometers, and the units of this number are nanometers Kelvin. So if I have an object with a certain temperature, I take 2,900,000, I divide it by the temperature in Kelvin, and that tells me, oh, at what wavelength I will find the brightest light. On the other hand, I can also reorganize this equation, and I can say, I can solve for temperature. Temperature is equal to 2,900,000 nanometers Kelvin, or the units of that constant, divided by lambda max. So this is what I use as an astronomer. I measure that brightest wavelength emitted by a star, and that allows me to calculate its temperature. This equation, the two different forms of this equation, is called Wien's law. W is pronounced with a V because he was German. And so what that means is if I had a star with a temperature of 290 Kelvin, so we have or maybe not a star, I have some city everyday household object with a temperature of 290 Kelvin. I take 2,900,000, I divide it by 290, and what do I get? Okay, we can cancel out this, we can cancel out that, and so that would be 2,900,000. They'll move the decimal plate 1, 2, 3, 4 places, and so this would have a peak at 10,000, 4 decimal places, 10,000 nanometers. An object with a temperature of 290 Kelvin, Kelvins cancel the constant, would have a brightest wavelength of 10,000 nanometers. Oh, 10,000 nanometers. That's off in the infrared part of the spectrum. Or similarly, if I want to measure the brightest wavelength here, I can use that to calculate the temperature. And I just put this at 2,900,000 divided by the brightest wavelength, as the lambda must be measured in nanometers. Then that allows me to then calculate what is the temperature of that object. And so that is one of the most powerful tools I have in astronomy. Wien's law and this relationship between brightest color and temperature allows me to then measure the temperature of every opaque object in the entire universe. And that's a powerful tool.